Greetings everybody. This video will again hopefully explain how to draw uh, the friction force. Remember we're looking at what I call the four most common forces. Weight, normal, tension, and now friction. Okay, now friction of the four, friction is the most difficult because there's two types of friction. Notice I have here, and again let me backtrack a second. We use a lowercase f to indicate friction. And there are two types of friction forces. There's what's known as static friction and kinetic friction. Hence, notice I have the subscripts Fs and Fk. Well, static means stationary or not moving. Fk means kinetic or moving. Well, so let's look at them in order. Well, static friction, Fs, that's the, for lack of a better way to explain it, it's the friction force that keeps an object stuck, i.e. not moving on a surface. Again, static means stationary. The idea is that an object will not move unless the applied force F is greater than the static friction force Fs. We're going to look at that more closely in the figure below. One example would be if you have, say, a piece of furniture on a hardwood or linoleum floor, maybe a couch, and you haven't moved, it hasn't moved for quite a while, and you decide you want to move it and sweep under it, clean under it. Well, initially, when you try, you're going to push it or pull it to slide it across the floor. Well, initially, you're going to notice some resistance. It's not going to move. And then once you sort of apply that little bit of extra force, then it begins to move. And then once it's moving, it's a little bit easier to then slide it across the floor. You have to overcome that Fs to get it to move. Once you do, it's a product of Newton's third law. Then once you get it to move, it's somewhat easier to move. But in other words, the applied force has to be greater than Fs for the object to even begin to move. Now, once it's moving, again, consider sliding that couch across the floor. Once it's moving, friction still exists. But because it's moving, the friction force, it's not Fs. It's a different friction force called Fk. And kinetic means moving. Well, in each case, what is the direction of Fk? Well, friction, as you know, think about it, it opposes the motion. So the directions of Fs and Fk, they're exactly 180 degrees opposite to the direction of the motion. So then now let's look at this figure. Well, and in general, Fs is greater than Fk. Well, let's look at this figure. I think it gives and then the resulting graph. Notice here you have your trash bucket, and this figure uses the lowercase n to indicate normal force. Don't let that throw you. It's Fn. That's the normal force of the driveway on the bucket. But in this case, what happens? You got your trash bucket. It's sitting at the edge of your driveway near your house or apartment. It's the trash people are coming the next day. You want to take this trash bucket and you want to push or pull it out to the edge of the road so that the people can come pick it up. So you're gonna have this applied force F, and you're gonna push or pull that bucket. Again, it's in your driveway, but typically until it's trash day, you keep it around the corner, but you keep it close to your house. You don't leave it out by the edge of the road. People are knock into it with their cars. So here, right now, you're trying to pull this trash bucket, and so you have the applied force F, and right now the bucket's not moving, so the friction force is Fs. Okay, so until the applied force F, until it becomes greater than Fs, the object will not move. Okay, so what's going on here right now? F is not greater than Fs, not moving. Eventually, when F is greater than Fs. Now notice in panel B, motion means, hey, the bucket begins to move. You're now pulling it towards the sidewalk, towards the road. And now notice here, once it's moving, the friction force between the bucket and the driveway is Fk. Notice Fk in this is clearly less than Fs. But notice in this figure, you're trying to pull the bucket, in this case, in the positive x. Well, the direction of the friction force, be it static or kinetic, is going to be exactly opposite. So in this case, Fs and Fk, notice they're in the negative x. Now, so what's going on? Well, let's look at this. Let's look at here, combining panel A and B. So what's going on in panel A is it's the static region, meaning right now until you hit the threshold of Fs, the bucket won't move. So here you're increasing the applied force, still no motion, so increasing large F, increasing F. When I say F, I mean the uppercase F, the applied force. So increasing F, no motion, so static. F is still increasing, static. F is still increasing, disco. Right here, when the applied force now equals the maximum friction force, so static, disco. Large F is now equal to the maximum static friction force. Now the bucket begins to move. So that's why this is the static region in A, and then now it's the kinetic region. Well, once the object begins to move, the friction force now becomes Fk. And the force required to keep it moving is now less than the force required, that peak right there. That's when F hits its maximum. Up until that, so F is increasing. F hits its maximum, which is Fs max. Then now at this point, the object begins to move. It's now the kinetic region, but the applied force F required to keep it moving drops down. It drops down by this amount right here. So, but in both cases, the applied force F is in the positive x, meaning that the friction force, whether it's Fs or Fk, will be in the negative x. Well, now here Fk is mu k times Fn. We'll get to that in a minute. Let's not worry about that right now. Let's look at how to draw some examples of the friction force. Okay, here's an example of somebody, they're skiing down an incline. And then when they get to the bottom of the incline, they continue to ski across the horizontal surface. Well, again, mg is the weight of the person. Fn, this is Fn, that's an I, meaning that's the normal force of the incline. Notice, I haven't drawn Fn going all the way through the person because I don't want the diagrams to get cluttered. But clearly, my normal force vector, clearly, it's perpendicular to the incline. Likewise, down here, Fnh means that's the normal force of the horizontal. Just to keep the diagrams clear, I haven't drawn Fn going all the way down to the bottom. But again, clearly, Fnh is clearly perpendicular to the horizontal surface. Okay. And again, mg in each case. Oh, darn it. mg, they're both exactly the same in the negative y. But now let's look at friction. Well, in each case, and now the dotted line, this indicates that the person is moving down the incline. So the dotted arrow indicates the direction of the motion. And in this case, I'm just saying he's moving down the incline with a constant speed, v, i.e. vi, meaning v incline. But notice there's friction. And again, unless you're told specifically that there is no friction, always assume there's friction. So notice, if he's moving down the incline, Fk is going to be directed up the incline. And notice that blue vector is clearly drawn. That blue Fk, clearly it's parallel to the incline. Okay? So, but again, why? Because he's moving down the incline, the friction force will be exactly 180 opposite to it. So Fk incline up the incline. Now when he gets to the horizontal, he's still moving. Again, this dotted arrow indicates, hey, this guy's he's moving. Well, if he's moving in this case, if he's moving in the positive x direction, the friction force Fk will be directed in the negative x direction. And eventually he comes to a stop, but we don't need to worry about that right now. But that's how you draw, in this case, the kinetic friction. Kinetic friction on the incline, call it Fki. Notice it's directed up the incline because he is moving down the incline. And clearly, again, if he's moving down the incline, the dotted arrow, notice Fk is clearly exactly 180 opposite. Here, if he's moving when he's on the horizontal, if he's moving in the positive x, Fk is in the negative x. Well, how do you calculate the magnitude of the friction force? We know how to get the direction. Well, whether it's Fk or Fs, friction force is always, I like to say, friction force is coefficient times normal force. So Fk is mu k Fn, Fs is mu s Fn. This is always true, 100%. Fn, as we know from not the previous lecture, but the one before that, Fn depends on the geometry of the problem. But friction force is always coefficient times normal force. Well, Dr. Gomez, what do you mean by coefficient? Well, notice mu k, that's the Greek letter mu, and the subscript k means that's the coefficient of static friction. Mu is the standard symbol for coefficient of friction. Mu s is the coefficient of static friction. Well, mu s or mu k, they depend on the two surfaces that are in contact with each other. You know, there's less friction for somebody skiing down an incline than there is between a car tire skidding on a road. So the coefficient of friction, the Greek letter mu, mu k or mu s, that coefficient depends on the two surfaces that are in contact with one another. Again, a surface in contact with snow is probably going to have much less friction than a surface in contact, with cement. It's going to be a lot difficult to slide down a cement incline than it would be a snow-covered incline. But so Fk is mu k Fn, Fs is mu s Fn. Always true, whether it's k or s. Friction force is always coefficient times normal. Fn depends on the geometry. In general, mu s is less than mu k. And mu k is the coefficient of kinetic friction, mu s the coefficient of static friction. They have no units, they're a coefficient. In math and physics, coefficient means it's just a number, it has no units. Well, how do you get them? Well, you look them up. And this table 5.1 gives some average values for first column is mu s, second mu k. Rubber on concrete, mu s 1, mu k 0.8. Notice mu k is less. And in general, whether it's static or kinetic, mu s or mu k, they're going to be less than 1. You'll never have a coefficient greater than 1. If you have a problem where it requires you to calculate mu s or mu k, if you get a value greater than 1, it means you messed up. But here, and again, how do you can look them up. And notice these values are what we call approximate, because when we say rubber on concrete, is the rubber, is it a motorcycle tire? Is it a bicycle tire? Is it a car tire? Is it a Goodyear? Is it a Goodrich? Is it a, whatever. But notice in general, mu s 1, mu k 8, steel on steel, mu s 0.74, mu k 0.57. And again, the larger the coefficient means the more friction exists. It's a quantitative measure of how much friction exists between two surfaces. And if you're getting coefficients of around 0.3, 0.4 and higher, that's a good amount of friction. Anything around 0.1 or lower, you're getting to be not a whole lot of friction. But you get the glass on glass, static 0.94, kinetic 0.4. Ice on ice, very little friction. Static 0.1, kinetic 0.03. Anything less than 0.1 is we say very little friction. Waxed wood on dry snow, 0.04 for the kinetic. Teflon, a non-stick, i.e. non-friction surface, 0.04. Synovial joints in humans, I believe they're like your elbows, your knees, your wrists, your ankles, 0.003 for the kinetic. But anyway, so that's that. We'll do some examples in the next section involving the coefficients. But how do you draw on the friction force? It's always exactly 180 degrees opposite to the direction of motion. In this sketch here, the dotted arrow indicates which way the person is moving. Here, he's sliding down the incline. Then when he gets to the bottom on the horizontal, he's now sliding in the positive X direction. So FKI, that means kinetic friction force on the incline. FK, that's the kinetic friction force on the horizontal. Notice in each case, it's clearly exactly 180 degrees opposite to the motion. How do you calculate it? Fk is mu k Fn. Fs is mu s Fn. Where do you get mu k mu s? Look them up. Alright. Let me go ahead and save this video and get it posted. And then we're going to do some number crunching, not to worry. But right now our goal is, of those four forces, weight, normal, tension, and friction, can we correctly draw them? Because if you can't draw them, because force is a vector, vectors have components, if you can't draw them correctly, there's no way you'll be able to solve these problems. And that right now, that's our goal. That's what you want to come away with at the end of this video. Can you draw those four common forces? Can you draw them correctly? And hopefully you can. Let me go ahead and save this video and get it posted.